All right, in this next section, we're going to be talking about some properties of determinants and some helpful things that we should know about determinants that might sometimes make it easier to calculate them. So what it says here is let A be a square matrix. So just to be clear here, that means that it's n by n. And the three following things happen. So it tells us basically when we do row reduction on a matrix. Let me start over. So in the last section, at the end of the last section, we saw that when you do the determinant of a triangular matrix, you just multiply the diagonal entries together, right? And so that's really nice and easy. And so the idea is if we can row reduce a matrix to make it triangular, then that's nice for the determinant. And so this basically tells us what happens when we do row operations to the determinant. So the goal is in these problems to row reduce something to make it triangular so that it's easy to do the determinant, and then use these properties to adjust the determinant as needed. The first one says basically, if you multiply one of the rows in A and you add it to another row, the determinant stays the same. That's what, right? So you're equal. It stays the same. It tells us if we switch two rows, so if two rows of A are interchanged to produce a new matrix B, then the determinant of the new matrix is -1 times the old one. So if we change rows, we need to multiply our new determinant by -1. And this one says if a row of A is multiplied by a number to produce a new matrix B, so it's multiplied by K, then the determinant of the new matrix is K times the determinant of the old one. Now, usually we're interested in the determinant of A in this one. And so the other way, if we divided K over the other side, the other way of saying this is 1 over K times the determinant of the new matrix is the determinant of the old matrix. So both these things are equivalent. Usually you end up using the second one. Because again, we usually want the determinant of the original matrix. You get it triangular, which is usually going to be B, and then you would multiply it by 1 over K if you happen to multiply a row by K. Okay, and so like it says, like I already kind of mentioned this, but it says it again here. The above theorem is helpful to do determinants because we know determinants of triangular is easy. It's just multiplying the diagonals. And so we can row reduce to a triangular matrix, just keep track of the row reduction things that happen, the operations, and then we'll multiply the diagonals and then apply the theorem to adjust for any changes made, any row operations. And so I'm going to use these three properties while we do this one here. And so let's compute the determinant of A in this one. And the idea here is we are going to row reduce this to make it triangular. To find the determinant. And we'll keep track of all the operations we do, and we'll apply the theorem above when we do it. Just kind of, well, let's just do it and then I'll say something about it. So determinant of A in this case would be the determinant of that thing. So I'm going to rewrite the matrix with straight lines around the edge because we know straight lines means take the determinant. Here I am taking the determinant. As a reminder, when we row reduce things, if we're row reducing, we want to sort of get a pivot in the upper left-hand corner, and then we use that 1 in the upper left-hand corner to cancel out the things below it. And so, for example, I'm going to use that 1, this first 1, multiply it by 2, and add it to the second row to cancel it out. So I'm going to take row 2, and I'm going to add to it 2 times row 1. And when I do that, I get this matrix. First row stays the same. The last row stays the same. The middle row changes. And the middle row becomes 0, 0, -5. And I'm going to keep track of what we did there because we're going to need it in the last step. So what we did was we added a multiple of one row to another, right? We did 2 times row 1, and we added it to row 2. Well, the theorem up top says when you do that, when you add a multiple of one row is added to another, the determinant stays the same. And so that operation we just did doesn't actually change the determinant. Let's fix my clipboard here. And so we added the multiple of one row to another. And so the theorem says that the determinant stays the same by theorem 3 above. Keep in mind, hey, that was helpful, and now we got a row with a bunch of zeros. And so one thing you could do if we just wanted to make it a little bit easier is we just did something that didn't change the determinant, and now you could expand around row 2, and that would be really, really easy to do. So that's sort of one nice thing about this. We're going to keep going with it, but just note that expanding around row 2 right now could be nice. But we'll keep going and make it triangular and just show you how the theorem works. Okay, so then I want to make it triangular. And so I'm going to put this one with two zeros. I'm going to switch rows 2 and 3 to put the zeros down at the bottom. And so I'm going to switch row 2 and row 3, and we're going to get this matrix. So the first row is not moving. I'm going to switch rows 2 and row 3. And what the theorem tells us about that, if we switch 2 rows, we multiply the new determinant by -1. So let's make note of that. So by theorem 3, we want to multiply our determinant by -1 once we get to that step. This is almost triangular, right? This would be triangular if this -1 was a 0, right? Because here's the diagonal. Above it is some non-zeros, and so we want below the diagonal be 0, so we just want to make the -1 a 0. So we can just take this one, add it to that one to make it 0. And so the last step in making a triangular matrix here is to do R2 plus R1, and that makes it into a triangular matrix. But we added 2 things together, and that doesn't change the determinant. So theorem 3 says that the determinant stays the same because we just changed, we just added rows. And so this is now a triangular matrix. And so it's nice and easy to do the determinant because the determinant of a triangular matrix is just the product of the diagonals. And so we can just multiply 1 times 3 times -5, but also keeping track of the things that we've done and the operations. And so the final determinant then, we just row reduced, we can get a determinant here of multiplying the diagonals together, but also multiplying by -1. So the first operation we see didn't change it. This operation didn't change it. The only thing that changed the determinant was when we switched rows 2 and row 3. And so we want to take this -1 from that and start with it. We're going to multiply by -1, and then we're also going to multiply the diagonals together. So it'll be -1 times 1 times 3 times -5. So we get positive 15 as our determinant. So that -1 became this -1, and then these 3 entries are just multiplying the diagonals. And so the only sort of penalty we got from doing that row operation was we needed to multiply by -1 because we switched 2 rows. And so this gives a nice-ish way if you have a complicated matrix, if you just do a little bit of row reduction, sometimes you can make the determinant easier. I mean, we already made it easier just on that first step by putting a couple zeros in there. We could have expanded around row 2, or we just could have kept going, do one more operation, keep track of the -1, and also get there. In my personal opinion, doing sort of row reduction and then doing the determinant isn't usually any better than just doing the determinant to begin with. Like we could have just started with this, expanded around the 3rd row or the 3rd column, and just sort of done the determinant directly. And it would have been no more or less work, possibly even less work, because if you do row reduction, you have to like row reduce for one thing. You also need to keep track of everything you're doing, and then you need to carefully row reduce, right? And so there's like potential to make errors when you do this method. And in my opinion, it's not you shouldn't always go to this. It's kind of something nice to know, but it's not something you should automatically go to. Okay, though, so let's look at a couple more examples here. So on the second page, you might see what's going on here already. Let's find the determinant of this. We're going to do the same thing, though. We're going to find the determinant by using row reduction to echelon form. So this is our matrix A. Let's row reduce this one again. Keep track of everything you're doing, and then see what happens with the determinant. So the first thing we've got our pivot in the upper left-hand corner. We want to use that 1 to get rid of the 3 and the 2. So I'm going to do that in one step here. I'm going to do row 2 minus 3 row 1 to get rid of the 3. And then I'm going to do row 3 minus 2 row 1 to get rid of the 2. And so when we do that, we end up putting zeros below that 1. And then the matrix turns into this in the other locations. And since we just added or subtracted multiples of one row with another row, we don't change the determinant. So no change to the determinant by part A of the previous page. Green might be a little brighter there on the bright. That's a little bit better, I feel like. That helps. Sorry, that first page is a little bright. Okay, so we didn't change the determinant. We almost have an upper triangular matrix. We just got to make sure that this 3 goes away. And so let's multiply row 2 by 1/6. Right, divide this by 6, make it into a -3, and then add it over there. And so I'll do that in 2 steps because I want to keep track of what's going on. So the first thing I'm going to do is do 1/6 times row 2, because that's going to make this entry into a 3. And then I'm going to use that -3 and add it here. But before I do that, I realize I multiplied a row by a number. And part B of the theorem on the previous page, part C, I mean, says if we multiply a row by a constant, we need to account for that in our determinant here. And so what we did here is we multiplied by 1/6. And so K in the theorem is 1/6. So keep that in mind when we keep going here. And now I want to use this -3 to cancel that one out. So I'm going to do row 3 plus row 2. And this doesn't change the determinant because we're just adding rows. So it doesn't change the determinant by theorem 3, but we end up with an upper triangular matrix. So we'll have 1, 5, minus 3, 0, minus 3, 2, 0, 0, 1. And this is now triangular. And so we can multiply the diagonal entries to get the determinant. But we need to keep track of this thing where we multiplied by 1/6. And so the determinant then of our original matrix is going to be the product of the diagonal, so 1 times -3 times 2. But then I need to apply the theorem. And so the determinant of the old one is 1 over k times the determinant of the new one. And so I need to do the 1 over k part, and k is 1/6. So I'm going to multiply this by 1 over 1/6. And so just to be clear here, this is the diagonals multiplying. And this part is 1 over k. And when we simplify that down, we get 1 times -3 times 2. When you flip the 1/6, you get 6. And so this ends up being 6 times -3 times 2. I'm sorry, I messed this up. This diagonal is not a 2. It should be 1 times 3 times -1 times 1. So this should be a 1 right here. Sorry, I picked off the wrong diagonals. Maybe some of you guys are yelling me in the video. This should be a 1. And then you get 6 times -3 is -8. So just to be clear here, this 6 came from K being 1/6 in theorem 3. Okay, and so the determinant of this matrix A turns out to be -18. Wonderful. Other types of problems you sometimes see related to these things are kind of looking like this, where it's like, oh, hey, we've done some row operations. Tell me what the new determinant is. So like on this one, you're being told that the determinant of the matrix here, A, B, C, D, E, F, G, H, I, is 7, right? So it's inside straight line, so we know that means determinant. And so in this new matrix, the rows have been switched around, and so we can figure out what's been going on here. So from here to here, we would get this matrix by switching, say, rows 1 and 2, and then switching the new row 1 and row 3. Right? So if you switch row 1 and row 2, those two would be switched, right? And so the A would be in the middle and the D would be on the top. And then you would switch the new row 1 with row 3, excuse me. And then switch the new row 1 and row 3. And so if you just switch rows a couple times, you can get from here to here. Hope you see what I mean by that. And the theorem basically tells us that since we switch rows, we multiply by -1 twice. Right? This one tells us multiply the determinant by -1 by theorem 3, and then we do it again here. Multiply the determinant by -1. And so the determinant of the new matrix is just -1 times -1 times the old one. So what we just learned here is the determinant of GHI, A, B, C, D, E, F is -1 times -1 times the determinant of the old matrix. And we know the determinant of the old matrix is 7 from the problem. So this is just -1 times -1 times 7. So it actually stays the same in this case, 7. Okay. Let's keep going. Let's look at a couple theorems related to this. So one of the things that we're going to talk about here is how the determinant is something that we can add to the invertible matrix theorem. So this says a square matrix A is going to be invertible if and only if the determinant is not 0. So this is an if and only if statement, so it works both ways. So in other words, if the determinant is not 0, it also means the matrix is invertible. And since we've got something related to invertible matrix, we can add this to the invertible matrix theorem. One second. Just wanted to check what was going on. Sorry about that quick delay. My daughter in the other room is having a little bit of a fit. I just wanted to check to see if everything's okay. It is. She's just 2. Okay. So I was going to prove this theorem, and it needs to be proved both ways. And so I'm going to prove the first one. I'm going to assume that. It also gives us a way to test for like linear independence and things like that, for example. So for example, I'm not going to prove it. I'm just going to show you. So it says this theorem provides a great way to test if the matrix is invertible. It also leads to this result. So let's suppose the determinant is not 0 of the matrix. This theorem tells us, well, that means the matrix is invertible. So the inverse exists. Well, if the inverse exists, that means you can use A inverse to solve a matrix equation, to solve AX equals 0. And so let's do that. So let's solve the system AX equals 0 using the inverse. Remember, if you want to get x by itself and you know the inverse exists, you can multiply on the left by the inverse, because A times A inverse cancel each other. And then you have A inverse times 0, so that just equals 0, right? So in other words, you get this equals the identity matrix, this equals 0. And so if the inverse exists, so if the determinant is not 0, that means the inverse exists, which means you can solve this, which means AX equals 0 has the 0 solution. In other words, AX equals 0 has only the trivial solution. And if we know that AX equals 0 has only the trivial solution, that means that the columns of A are linearly independent. That was the definition of, that's how we found and tested for linear independence, is seeing whether or not we have a non-trivial solution. And so you can see how these things get tied together, right? These are a lot of the things that are in the invertible matrix theorem, and we're just kind of showing how they sort of lead to each other. If the determinant is not 0, it very clearly leads to columns being linearly independent, for example. And vice versa, the flip of that is, if the determinant is 0, we can also show that the columns are dependent. So for example, alternatively, if the determinant of a matrix is 0, then that means the inverse doesn't exist by this theorem. And if the inverse doesn't exist, then the homogeneous solution AX equals 0 has a non-trivial solution. And if we have a non-trivial solution, we have linear dependence. And so, when I teach this class and we use we do homework out of the book, we use this idea in homework from 3.2, number 25. So if you want to look at that one from the lay book, this is the idea you use in the homework. I don't remember if this is in the online homework or not. I honestly can't remember. But if you look at number 25 in 3.2, this is the kind of idea you use on problems like that. But anyway, what we're going to end up doing is tacking this onto the invertible matrix theorem, right? So if a determinant is not 0, it means the matrix is invertible. A couple other theorems here. So the first one's telling us for a square matrix, the determinant of the transpose is the same thing as the determinant of the regular matrix. So let's remind ourselves what the transpose means. So when you have a matrix, let's do a 3 by 3, A, B, C, D, E, F, G, H, I. When you take the transpose of a matrix, when I put a T like that, like it is right here, the rows become the columns. And so the first row becomes the first column. So it'd be like A, B, C going down this one, right? Second row becomes the second column. Third row becomes the third column. And so, in other words, when you do a transpose, you're just sort of like rearranging the columns and the rows. You're not changing any entries. They still are in the same order. And so since you can expand across any row or any column, the determinant stays the same, right? In other words, expanding across this row ABC is the same thing as expanding across this column. And so we get the same answer when we do the determinant of the transpose. The last piece here just says that if we have two square matrices, then the determinant of their product is the product of their determinants. And so in this explanation here, A times B is a product. It's two matrices being multiplied into a new matrix. And so if we have a new matrix A times B, and we're doing the determinant of that, we can just split it up and do the individual determinants. And so this gets used in a couple of sort of places. So one application of this is if you have if you know the determinant of the matrix is 6, for example, and then you want to know the determinant of 3 times that matrix or something like that, then So we know the determinant of A is 6. We want to know the determinant of 3A. Well, this is just the determinant of 3 times the determinant of A. And the number 3 you can think of as like a 1-by-1 matrix. And so the determinant of 3 just stays the same. It's just 3. And we know the determinant of A is 6. And so that's sort of one application. If you want to do a scalar multiple of the determinant, you just scale the determinant by that multiple. The other way you kind of see this sometimes is if you have like the determinant of B cubed, then you're just going to split this up into determinant of B, determinant of B, determinant of B. So you're going to get determinant of B cubed. And so just to be clear, this is telling us, this property is saying you can split up the product of determinants. This one comes up a lot when you're doing proof type things, just to be clear. Okay, there's one other thing on the last page we should look at. It's an in-class activity. I would encourage you to take a minute and think about what each of these things are before I go over the answers. They're pretty quick. Like if you kind of understand what's going on here, these should be very quick answers. And so I would take a second and try them, maybe think through it really quick. Again, should maybe take you no more than 5 minutes, I would say, to try these. So pause the video and give that a go. I'm going to explain them right now. So let's call this matrix A. What we're being told here is that the determinant of A is 7. Right? That's what this is saying. And so using that information, we can calculate these two determinants. So this matrix, right, this row is the same, this matrix is the same as that one, except this row has been multiplied by 3. And so we multiplied row 2 by 3 to get this matrix. And so looking at the definition on the first page, K is 3. Thus, if we want the determinant of our new matrix, let's call this matrix B. The determinant of B is going to be 3 times the determinant of the old one, which is 3 times 7 in this case, which is 21. Right, so the determinant of this new one is 3 times the old one, again, using that information on the first page here. This matrix B, let's also call this matrix B. This is the same as that above matrix, except it's the transpose. So this is the transpose of the above matrix. In other words, if you did the transpose of the matrix A at the top here, you get B. And what we just saw in the theorem on the last page is that transposes have the same determinant. And so since the determinant of A is the same as a transpose, this means that the determinant of B is the determinant of A, which is 7. Okay, last two are also really, really straightforward. I hope you'll agree. So if we know the determinant of A is 4, what's the determinant of A to the 5th? Well, we know that we can break up determinants, right? So determinant of A to the 5th is determinant of A times itself 5 times, which we can break that up 5 times. So determinant of A, determinant of A. There's 3, there's 4. That's 6. 1, 2, 3, no, that's 5. And so we just multiply 4 by itself 5 times, right? 4 times 4 times 4 times 4 times 4, or 4 to the 5th, which is 1024. And then the last ones at the bottom of the page, use the determinant to see whether or not these have an inverse. So we just look at the inverse and see whether or not it's 0. And these are 2 by 2s, and so the inverse is really easy, right? The determinant of A is going to be AD minus BC, which is going to be 1 times -1 minus 3 times 2. So we'll get -1 minus 6, which is -7. And so since it's not 0, it has an inverse. I think on the next one, we're going to get a 0. So if we do determinant of this one, we also do AD minus BC, but in this case, we get 6 minus 6. So we get 0. And so B does not have an inverse since we get a 0 determinant. Okay, so some nice sort of straightforward, hopefully, applications of determinants and how we use them in practice. I'll just sort of close here by mentioning there are lots of interesting applications of determinants. I know I put this really long link on here, but if you just like Google this person's name right here, they have some really interesting applications of determinants on their website, some very advanced things that are kind of beyond the scope of this class. But if you're interested in this kind of stuff, take a look. I'd be happy to talk to you about that and maybe look through it together. All right, thanks, guys.